So what we will do today is we will briefly go over classifiers using the idea of artificial neurons. So we call these classifiers as neural classifiers. So these are built using artificial neurons. These classifiers are pretty powerful. And these classifiers can produce arbitrarily complex decision boundaries, just like you can get arbitrarily complex decision boundary in the case of k nearest neighbor classifier. All right. On top of that, if you use these classifiers with the idea of end-to-end learning, where the features are also learned by the network and not specified by the user, in that case, you end up with very powerful systems. And these systems are basically based on what we call as deep learning. So deep learning, which is currently very popular, is an extension of neural classifiers. In the case of neural classifiers that we will be discussing today, we will assume that you have a collection of training examples where each training example has certain number of features and it has a class label associated with it. In the case of deep learning, the features are also learned by the network. So all you do is throw the raw data at the network. As an example, for a deep learning system, if you wanted to build a system that could differentiate between pictures of, let's say, different animals, then what you will do is you will basically throw a large collection of those pictures. For every picture, you will tell the network, well, here is a picture of a cat, here is a picture of a cow, here is a picture of a dog, and so on and so forth. And network on its own will try to figure out what differentiates pictures of cats from pictures of dogs and cows. In the case of neural classifier, what you will do is you will basically take that collection of pictures and you will think about some kind of a scheme that will allow you to extract certain features from those pictures, with the idea that those features will be useful to make a distinction between different animals. And then you will feed those features to the neural classifiers. So in some sense, with neural classifiers, as a designer, you do half the work. You do feature extraction just like we do in naive Bayesian or KNN. But with deep learning, you don't do any work, you throw everything at the system and the system figures it out. All right, so we will just limit ourselves to simple neural classifiers. And these classifiers obviously are motivated by biological neurons. Right? Just to give you an idea of how complex is the brain, a human brain has about 10 billion neurons. And each of these neurons is connected to about 10,000 and more other neurons. So basically, you have a system which has billions of neurons, and the system has a lot of connectivity. That is, each neuron is connected to a very, very large number of other neurons. So in some sense, you can say, all right, such a large population of neurons, heavily interconnected, together they try to collectively solve the problems. All right. The similar idea is used in the neural classifiers or in neural networks, except that we are not going to the level of 10 billion neurons and things like that, but we work with much fewer neurons, but the ideas are the same, all right? And in the case of a biological neuron, each neuron receives electrochemical input. Basically, you have to remember that it's the These are the chemicals that create disturbances or intelligence in the brain. So these neurons get their signals, which are electrochemical signals. And when the net value of the signal arriving at a particular neuron input exceeds a certain threshold, the neuron fires. And when it fires, obviously it sends its output signal to the neurons it is connected with. And that's how, the things propagate in the in the human brain. All right. So picture here shows you how, a neuron looks like and what are the parts of a neuron. All right. So that's the basic idea. And based on this idea of biological neuron, way back in somewhere around 1945, these two scientists, McCullough and Pitts, they created an electronic model for the neuron, and obviously it was called McCullough-Pitts neuron model. This neuron model basically looks as shown in the picture here. So you assume that there are a number of input signals to the model. In this case, the signals are X1 to XP, so there are P signals. Then there is a bias term coming from X0, which is always 1. So neuron is operating at certain power level. So you can say the bias term is kind of battery that you provide to the neuron. And these signals, as well as the bias, these things travel through certain wires or certain paths. And as these signals go over those paths, these signals get multiplied with the weight values that are associated with those paths. So at the neuron, it calculates the sum of or weighted sum of all the input signals it is getting. And that weighted sum, you can say, is nothing but a summation over 0 to P, because you have P input values and 0, and you have a bias. So basically you have P plus 1 input signals, all right? And corresponding to every input signal, there is a corresponding weight value, which is assigned to the particular path that signal is traveling. So the weighted sum is what this summing junction calculates. And if the weighted sum is positive, you can say the neuron fires. If the weighted sum is negative, the neuron does not fire. All right. So that was the model for an artificial neuron inspired by the biological neuron proposed way back somewhere around 1945. All right. So you can see that we can represent this net sum as simply net value or net input, and then compare it against the threshold and get either 0 or 1 as the output. Just to give you an idea how these calculations are done, I have a very simple example here. So you can see that we have a number of input signals and their values are specified here. And also specified the weight values, which are shown in the second column in blue. So you can see that we are calculating the net sum, which is being taken as the input value multiplied by the corresponding weight values. So you get the net sum, and then that sum is being calculated and compared against the threshold value. And that tells us what will be the output. All right, so in this case, if the value is greater than the threshold, output will be 1. If it is less than, the output will be 0. All right, so that's how really a simple neuron works. All right. The threshold function in that model that I showed you in the previous slide, that function is known as the activation function. So basically, there are two things going on in a neuron model. There is a summation going on, or weighted summation going on, and that summation is being passed through some kind of activation function. And in the original model, the activation function was a unipolar threshold function. A unipolar threshold function means it has only two possible values, 0 or 1. So when the signal or the net sum increases the threshold, output is 1, otherwise output is 0. All right. One can also have a linear function as an activation function. All right. But if you think about that, you will find that a linear activation function is of little use, except for certain cases where you may like to use it. A linear function really does not provide you much flexibility in doing things that you want to do. All right. So typically what you want a function which is nonlinear. So the function that was popular and is still popular to some extent is known as the sigmoid function. So the sigmoid function looks like an S curve. It's kind of moving from minus. For a highly negative value, it has a 0. The value of the function is 0. And for a highly positive number, the function value is 1. And of course, it approaches 1 and 0 in an exponential fashion. Okay. So the formula for sigmoidal function is simply output, which is the output after the sigmoidal function is given as 1 divided by 1 plus e to the power minus net, where net is the summation that the neuron is doing of all the inputs and the bias by weighing each term appropriately. All right. So this sigmoid function, as I said, was very popular up until about 28. And this function is also known as logistic function. So there are two names, sigmoidal or logistic function, both mean the same thing. And since 2008 onwards, this function is not as much popular because people have found that in deep learning, if you use a slightly different activation function, things turn out to be much better, much faster, much quicker. All right. So for neural networks that we are going to be dealing in this course, sigmoidal is pretty good, pretty fine. But if you want to go into deep learning, then you need to change your sigmoidal function. All right. This sigmoidal function also is a unipolar function in the sense that the output is in the interval of 0 to 1. All right. You have a question? Yes. Well, as you can see that you are doing the net sum, all right? And that net sum is going to be passed through some function, okay? Because if you don't pass it to some function, then you have no limit on the output. Because you are calculating all the inputs multiplied with their respective weight values. All right. So that sum can be anything. All right. By putting an activation function, what you're doing is you are limiting that output in a certain range. All right. In the case of threshold function, you are limiting into only two possible values, 0 or 1. So if you think of building a classifier, a binary classifier should have only two outputs, 0 or 1. So that's how it kind of maps there. Right.
Like X and weight, we are doing a summation. This summation, we are doing a summation. Could we use any other?
Yes, I think when people started playing with them, there is a slightly different model, which is instead of doing weighted sum, basically they calculate a product. If you look at the history of neurons, and I don't know how much you are familiar with the Boolean algebra. If you look at the Boolean algebra and you want to talk about the logic and logic functions and logic expressions, there are two approaches of expressing logic functions. One is called sum of product forms, which is what the model we are doing is using. It is the sum of product form, because if you look at each individual term, it is W1 X1 plus W2 X2. So it is a sum of product. All right. But there is another way of expressing the same logic through product of some form. Okay. So you could use that logic also. It turns out that people tried both of them, and this seems to be much more convenient and better. All right. So, but you can certainly try something different. All right. So that's what this sigmoidal function is. It's an activation function. All right. Now, in this case, the range is 0 to 1. All right. Sometimes you want a range minus 1 to 1. All right. Both are possible, and they still give you, finite interval. So you could have a threshold function, which is a bipolar threshold function. That is, if the sum is less than the threshold, output is minus 1. And if the sum is greater than the threshold, output is plus 1. All right. So that will be a bipolar threshold function, which is also called as a sine function. Yes, please. Wait. Just hold on, okay? And if you look at corresponding function that you may want to use instead of sigmoidal function, where the output will be in the interval of minus 1 to plus 1, then you can use what we call as a hyperbolic tangent function. So that is shown in the slide here on the right-hand side. And the hyperbolic tangent function has a form 1 minus e to the power minus net divided by 1 plus e to the power minus net. So if you use that function, you basically end up output in the interval of minus 1 to plus 1. And again, the minus 1 and plus 1 values are approached slowly. And the function looks something as shown here. Kind of, again, S curve, but ranging from minus 1 to plus 1. All right. Now, in practice, again, if you look at the comments there, that is, in this case, the output is zero-centered, and it turns out that using hyperbolic tangent function, you get little better results, let's put it this way, all right? So again, it's up to you, but people try both of them, all right? So that's what we mean by activation functions. So with that, let's look at a simple classifier that you can make using the idea of neurons, all right? So a simple classifier using just a single neuron is known as the perceptron classifier. So this was the classifier that was proposed somewhere around 1950 to 55. So it's about somewhere about 70 years ago. All right. So what does this classifier look like? Again, if you look at the picture, basically you have a bias line, and then you have x1 to xn, n input signals or n features that you have. So you feed bias as well as these n features to a sum unit. And of course, when they are reaching at the sum unit, they are facing these weight values, so they get multiplied by these weight values. So at the sum unit, you are calculating this expression, which is summation over I equal to 1 to D. If you have D features, I think I'm showing you N. So basically that should be N. All right. So just, a little mistake there. Wi xi plus W0. So W0 is the constant or the bias term. And Wi for all different I values are the respective weights that you assign to different features or different input lines. All right. And then this is fed to the step function, as we saw earlier, a threshold function. All right. And you can say that if the net summation is greater than or equal to 0, output is 1. If the net summation is less than 0, the output is -1 if you're using a bipolar step function. All right. So basically, that's how a classifier looks like. All right. So you can see that last time I mentioned the idea of a discriminant function, a gx, which will produce you positive or negative values depending on the class of the input signal. Basically, this is nothing but the discriminant function, except that we are putting it in the form of a perceptron classifier. All right. And since this is a linear function, so if you were to look at a decision boundary that this classifier will produce, that decision boundary is going to be a linear boundary. All right. And if you look at the different weight values, this quantity W0, or we call it as a bias weight will determine where you locate your boundary. And the other weight values will determine how the boundary is oriented. So if you are looking at a problem in 2 dimensions, the bias weight will tell you where the boundary intercepts the x and y, x or y axis. And the orientation of the line will be given by the other weight value. All right. So same thing happens in higher dimension. So W0 will tell you where the hyperplane is located, and the rest of the parameters will tell you what is the orientation of the hyperplane. So now we come to the question that you were asking earlier: how do we get hold of these weights? All right. So basically, we assume that we are given a collection of training examples. And these training examples come from 2 classes, because we're trying to build a system for binary classification. All right. So these weights are determined by an algorithm which is known as the perceptron learning algorithm. As I mentioned earlier, this perceptron classifier was proposed somewhere around in 1955 or close to that. So that is the time when this algorithm was proposed. So it was suggested that if we follow this algorithm, we can actually learn these weight values. All right. So it's about 70-year-old algorithm. All right. Now, what are the characteristics of this algorithm? It's an error correction algorithm. What do we mean by error correction algorithm? It means that we will be presenting to this algorithm examples one by one. And when it looks at an example, the algorithm will try to predict whether it thinks the example is from class 1 or class 2. And if the answer is correct, that is, the prediction by the algorithm matches with the actual class membership of the example, then we say that no error has occurred. All right. So the algorithm doesn't do anything. It's happy that it did a good job. All right. But when an error occurs, say for example, it says it is from class 1 and it turns out the actual example is from class 2. So then an error has occurred. So what the algorithm will do is it will try to adjust the weight values to correct for that error. So that's why it is called error correction algorithm. All right. And let's look at this algorithm first through an example, and then I'll give you the actual algorithm. All right. So perceptron learning rule or perceptron learning algorithm, whatever you want to call it, uses training data from two classes. One thing you do is you augment the training vectors by adding an extra 1 to every training vector. And that extra 1, either you add to the head of the vector or you add to the tail of the vector, but you have to be consistent and figure out where you want to add it. All right. So after adding 1, basically what you have is augmented vectors. And the reason you add 1 is basically by doing that, you are able to take care of the bias term. So if you have 2 features and then you have, so basically you will have 2-dimensional vectors. But if you want to have a bias also in your calculations, then you can treat bias term as a 3rd feature with a constant value of 1. So that's why you augment it with 1. And what you do is you basically say, all right, let me just randomly pick some values for these weights, and I will initialize using those random values. And then compute the output for each training example one at a time. All right. The output will be calculated as we saw earlier, that formula. You calculate the weighted sum and run it through the threshold to see whether it is producing the right output or not. If the output matches, nothing is done. You leave the weight vector as it is and move to the next example. If the output is not correct, then we modify the weight vector. And the modification is done either by adding to it or by subtracting from it the current training example that is being misclassified. The reason we add or subtract is that if an example is from positive class or class 1, let's call that positive class. And for that example, the perceptron should have produced a positive output so that thresholding is done properly. All right. If it is not produced, that means we need to increase the output. And one way to increase the output is by adding the current training example to the current weight values. So that way the weight values will go up and you are pushing your example towards the correct side. And for the other class, the example from the negative class, if the output is not correct, that means you're getting more output than you should be getting. So what you want to do is you want to push it in the negative direction. So basically, you either push the output in the weight vector in the positive direction or negative direction, depending upon what kind of mistake is being made. And if you do it sufficiently by going over your training examples again and again, at some point, you will find that you have the correct weight vector. And of course, you don't present the examples in the same sequence. You always shuffle them so that the order of presentation is not the same. So that's basically the learning rule. Let's look at this rule in terms of a very simple example. So suppose we have two positive examples. Let's call them example A and example B. The example A has two features. Both features have values of 1 and 1. Example B has two features. Values are 2 and 3. The negative examples are C and D, with the respective features being 3 and 1 and 4 and 2. All right. So basically what we want to do is, given these 4 examples, 2 from each class, we want to figure out a weight vector such that when we use that weight vector, we get a positive answer for A and B, and we get a negative answer for C and D. If we can do that, then you can say that we have figured out a good weight vector for our problem. All right. Now, we need to have a bias term. So first thing we do is we add an extra 1 to all these vectors. So we augment them. So A becomes 1, 1, 1, B becomes 1, 2, 3, C becomes 1, 3, 1, D becomes 1, 4, 2. All right. So we added 1 at the beginning. All right. Let us assume that our initial choice for the weight vector is 1, 1, 1. All right. So with that initial choice, let's throw example A to the weight vector or to our classifier and see what is the output we get. So basically all you have to do is to do the dot product between the weight vector and the A, or W1 A first component plus W2 second component of vector A, W3 plus third component of vector A. All right. So if you do that product, basically in this case, the result is 3, all right, which is a positive result. So we expected positive, we are getting positive result. So no error. So we move on and present example B. In this case, the result is 6. Again, everything is looking good. We wanted positive, we got positive. All right. Now next we present example C. In this case, the output is 5. Now it should have been negative, but we got positive. So what we need to do is we need to decrease the weight vector value. All right. And to do that, what we do is we subtract vector C from weight vector. So what we'll do is we will subtract that. So we correct the weight vector, and after subtraction, the new weight vector becomes 0, minus 2, 0. All right. With that, we now present example D. And with example D, we get negative results, which is what we expected. So everything is fine. Then we go back and present example A again. When we do that, we get negative result. Now for A, we should be getting a positive result. So what we need to do is we need to apply correction. In this case, we need to add vector A, which is being misclassified, to our current weight vector. So when we do that, the resulting weight vector is 1, minus 1, 1. Now we present B, output is positive, that's fine. When we present C, output is negative, that is fine. When we present D, output is negative, that is fine. When we go back and present A again, output is positive, that is fine. That means this current value of the weight vector is able to give us the right answer for all the examples. So at this point, we can terminate the training and say we got the solution. All right. So basically, the algorithm is a very simple algorithm, as you have seen. All right. And although I presented these examples in the same sequence, but in practice, you will be shuffling them and presenting them in a random order. And basically, once you go over all the examples without making any changes in the weight, then at that time you can terminate the algorithm, because at that time you are able to correctly classify all the examples. All right. Now, it turns out that this algorithm will terminate only if the examples are linearly separable. That means you have a problem, classification problem, where the data from two classes is distributed in such a manner that one can draw a line or a hyperplane between two sets of points from two classes, and you will not find any error taking place. All right. So those are linearly separable examples. That means this is a good system when you know that you have a linearly separable data. All right. Now it turns out that if you are working in 2 dimensions, you can plot and you know, okay, or even 3 dimensions, you can get a good idea. But if you are working in 10 dimensions or 20 dimensions, there is no way you can look at the data and say, well, it's linearly separable or not. So if you apply this method and the underlying problem is not linearly separable, what will happen is that this algorithm will keep on working. It will keep on trying to correct the error, but it will never stop because there will always be some error because the problem is not a linear problem. All right. So that is the deficiency, you can say, of this method. All right. So if you want to put it in a slightly different way, you can say, all right, we are trying to find weight vectors such that they satisfy these conditions. To start with, we have 2 conditions. In one case, we want the output to be positive. For another class, we want the output to be negative. All right. As I said, we augment. So we do augmentation of every example. And then sometimes what people do is they will convert these 2 conditions into a single condition. If you take the second inequality and multiply it with -1, then the sign for inequality can be inverted. So instead of becoming less than 0, you can say greater than 0. All right. And the class label for negative examples is -1. So what you can do is you start with your vectors, augment them, and then multiply every vector with its class label, assuming that you are using 1 and -1 as labels for your 2 classes. So for positive classes, when you multiply with 1, nothing happens, no change. All right. With the negative class, multiplying with -1 means everything is negated, which in terms of the inequalities is inverted, and you end up working with a single inequality to build your classifier. All right, so that's how in practice it is done. So with that, if you want to look at the steps in a formal fashion, how this algorithm works, those are the steps that are given, and one can very easily write a small piece of code that will actually work and do this job. All right. Now you might be wondering, how did this algorithm was invented? All right. So just to give you an idea of how this algorithm was invented, or how we end up at this algorithm, the basic idea is that with this notation that I showed you in the previous slides, one can define some kind of cost function, which is shown here. So cost function J of parameter vector A, which is our weight vector, is nothing but sum of all misclassified training examples and minus A transpose Y that we calculate. All right. So basically what happens is, with this negative negation we have done, so every example is supposed to produce positive output. So misclassified examples will give us negative output. And with an additional negative sign, the criteria will be positive if there are some errors. If there are no errors, then the criteria value will be 0. So what you may want to do is you may want to optimize or minimize this criterion. And by doing so, we will end up with the desired weight vector. All right, so that was the idea that was used to build this algorithm. All right, the minimization is carried out by the gradient descent, which is nothing but an iterative method for finding minima of functions. All right, everybody is familiar with the gradient descent. All right, basically you start with some arbitrary point as a solution and then take the derivative, partial derivative of the function that you're trying to optimize and use that derivative to calculate the direction in which you want to move, and you have a learning rate that you allow to come up with a new set of values, and you keep on repeating that process. And if your cost function has only a single minima, then your gradient search will take you to that single minima. If your cost function has multiple minimas, then your gradient search will take you to one of the minimas depending upon where you start the process. All right, so that's basically, all right. So one can then, write down the learning algorithm through optimizing the criterion function in this particular fashion, which is basically what I showed you in the numeric example. All right. So that's how this classifier works. All right. Now let's look at what happens when the examples are not linearly separate. As I mentioned earlier, there is no way to figure out whether the examples are linearly separable or not. So you have to run the algorithm, and if it keeps on running and running and running, that means the examples are not linearly separable. All right. So question is, what do we do in such a case? All right. So there are two possible ways to deal with that situation. One is, instead of using a single neuron classifier like we have looked at, we use more than one neuron for classification. And we put them in layers. So we take one or more neurons, take their output, feed that output to the next set of neurons, take their output, feed that to the next set of neurons, and so on. And it turns out that if we have layers of neurons, then we can deal with problems that could be nonlinear problems. So that's one way of doing. The other possibility is to modify the optimization criteria. See, the optimization criterion for perceptron learning is error correction. You want to get a situation where you have 100% accuracy. All right. There are no errors. Now, instead of working with a criterion that is error correction, we might work with a criteria which is error minimization. That is, you assume that, okay, some error is going to happen. So why not we look for a weight vector which will minimize that error? So in an error correction, you're looking for a weight vector that will not give you any error, which may or may not be possible. But if you say, I'm satisfied with a weight vector that gives me minimum error possible, then that minimum error could be 0 if they are linearly separable, and it could be something very small when the examples are not linearly separable. All right, so both these possibilities are open to us. So let's look at them. So let's look at what is the idea of using layers of perceptron. All right. So let's take a very famous or very popular example, which is called exclusive OR logic. So basically you have 4 observations, and these observations are sitting at opposite ends. So for example, as shown in the picture here. So you have examples from class A and you have examples from class B. And class A examples and class B examples are sitting diagonally opposite to each other. All right. That means if you look at these 4 points, there is no single line that you can draw which will separate A from B. All right. However, you can draw 2 lines such that between the 2 lines, you will have examples, let us say from class A, and outside those 2 lines, to the top and the bottom of those lines, you will have examples from another class. All right. So in this case, a single line is not possible, but through 2 lines, you can at least get this much of separation. All right. Now with 2 lines, you can get an answer whether a given example is within that shaded area or a given example is outside the shaded area. All right. And what you can do is this information, then you can pass on to the next neuron, and that neuron can then decide whether it should produce an output of 1 or output of 0. All right. So basically, with 2 layers of neurons, you can tackle this problem. So you can look at this problem in this way, that you have your original data, then these 2 lines that you are creating through neurons, these 2 lines are actually new features that you are creating. And based on these new features, then you have another neuron that's able to do the classification. All right. So if you follow this, you can say, all right, we are talking of some intermediate output, and then we are talking of final output. All right. So this arrangement can be shown in this particular form. So you start with X1 and X2, which basically tell you the 2 values for A or B. All right. You feed them to 2 neurons, and the output from there will tell you whether the input is within that gray area or outside that gray area. And then you can make that decision with the second neuron in the second layer. All right. So basically, in this case, you are using 2 layers of neurons to get the job done. All right. So this idea that you can map the input through some intermediate representation through 1 or more layers, and then make a classification of that intermediate representation. And you could do this with 2, 3, 4, 5 layers, depending upon how complex your data is. All right. So this idea you can actually extend, or at least I can give you another example here. That is, suppose you want to build a classifier, again in 2 dimensions, just to keep the discussion simple, such that if a point is sitting in the yellow area, it will be classified as coming from the yellow area. And if it is outside the yellow area, it will be classified as coming from outside the yellow area. All right. So in this case, you can see that the decision boundary, the yellow area versus the rest of the area, is not a linear boundary. It's a nonlinear boundary. Number 1. Number 2, the 2 yellow regions are disjoint. They are, joined at one tip of the point. All right. So in this case, if you just think about it, you can use one set of neurons to create lines, because every perceptron, a single perceptron, basically is drawing a line in 2 dimensions if the example is in 2 dimensions. All right. So you can actually use 5 perceptrons in the left-hand side of the network, to draw 5 lines such that those lines will match with the lines of the bigger polygon. And then you can use in the right-hand side of the diagram another 5 neurons with 5 lines that will match the top polygon. And then the output of these 2 neurons or these 2 units can be combined using a neuron which implements an OR function, which combines these 2 areas and basically gives you the classifier that you want. All right. So basic idea is that you can have multiple layers of perceptrons to create any arbitrarily complex decision boundary. In fact, there is a mathematical proof which says that these neurons are universal approximators, and you can approximate any arbitrary function using one or more layers of these neurons. All right. So in this picture, I'm showing you what happens if you have a single layer or 2 layers or 3 layers. So if you have 3 layers, you can get fairly complex boundaries as well as regions which are disjoint regions. That means you can solve any classification problem using 3 layers of neurons as shown. All right. The question is, how do we figure out, because for the simple example in 2 dimensions, you can look at it and figure out what should be the weight values for those lines. But again, for real problems, you need to have a method which will figure out the weight values for all the neurons in all the layers. Okay. So that is where the NeuralClassifier design is in. All right. So before we go into that, let's look at the other approach where we said, all right, what we can do is we can modify the criteria and see if we can get things taken care of. All right. So let's look at what we call as a sigmoidal neuron. So basically a neuron where the activation function is a sigmoidal function. So basically you have a set of inputs, you have a bias, there are weight values assigned to different lines. You get a net sum of input values and bias through the respective weights, and you feed that net through an activation function. And the output of the activation function is what you will use as your, for your result. All right. So in this case, if we look at it, we can say y hat, which is the output that we are getting, all right, is equal to 1 divided by 1 plus e to the power minus w transpose x. All right. So that is the formula for the output. As I said, in perceptron learning, the criteria was focused on misclassified example. All right. In this case, we want to minimize the error. So let us focus on what we call as a mean square error loss function, all right, which we'll define as the difference between the desired output and the output of the summation feeding into the sigmoidal function. So let's define a criteria as shown in this expression. And 1 by 2 is just for getting rid of 2 in the calculations. All right. So JW, our criterion function, is 1 by 2 summation over all the examples. YI is the desired output. This is the output that you want. So this will be the label of the input example, minus W transpose XI, which is the activation sum that your network is producing. So you want to take the difference between the two, square it up, and add it over all the examples. All right, so that is your criterion function. So what we want to do is we want to find a weight vector W that minimizes this criterion function. And one way to do that is to take the partial derivative of our criterion function with respect to weight vector, and then apply gradient search using that partial derivative to get the solution. So let's do the partial derivative. So if we do that, del J by del W, if you do the simple differentiation, partial differentiation, the expression becomes minus. So now you can see that 1 by 2 has gone. That was the reason I had 1 by 2. All right. So minus sum over I equal to 1 to n yi minus W transpose xi times xi. Okay. Now, this is the value of the gradient over all the examples. All right. So when we apply gradient search using all the examples to figure out the next value, that search method is called batch mode. That is, we are looking at the entire batch of examples and calculating the differences, calculating the error, and then making the correction. All right. In certain situations, batch mode is fine. You can work with it, especially if the number of examples is not too many. But typically what people like to do is to do what we call as an online mode or incremental mode. That is, you look at one example, get the error, make the correction, get the next example, get the error, make the correction, and so on and so forth. All right. So if we rewrite the formula, all right, and if we rewrite for the online where we are looking at only one example at a time, so in that case, that summation sign disappears and del Ji divided by del W. All right. So now we are looking at the value of the criterion function with respect to the ith example. All right. So that formula on the right hand side turns out to be minus yi minus W transpose xi times xi. All right. So basically, what one can do is one can use this value of the gradient to figure out what should be the updated value of the weight vector. So you can write the formula for updating. You can say the new value for weight vector W new is going to be the current value or old value. So W old plus alpha. Alpha is our learning rate. So you can say, all right, alpha is the learning rate multiplied with whatever is the gradient value we got. All right. And since we are trying to minimize, so we will be subtracting the gradient. That's why you can see that that negative sign I had in the formula up in the first line, that now is not there, and now we are adding it because we are moving towards the minima. All right. So that's why we are doing that. So this is the formula that one can use to get the updated weight value. And if you keep doing this, at certain point, you will find that the weight value stops changing, or the change in the weight value is really, really very small. At that time, you can say, well, I can stop now because I got the optimal weight vector that I need, and your job is done. All right. So this rule is known as, it's got a couple of different names, people use it. It's called Woodrow-Half rule. That was the rule which was proposed, I think, somewhere around 62, about 60 years ago. It is also known as the LMS rule, least mean square rule, because that's what you're trying to do. Or it is also known as delta rule, because when we look further, you will find that we will introduce a term delta. So basically that term is tied up with this particular expression. So that's why it's also called delta rule. All right. Alpha is called the learning rate. Typically it should be very small, generally 0.1 or so. All right. So the important point to remember here is the difference between error correction and error minimization. So error correction may never cease, but error minimization will definitely cease. All right. So that's the difference you have to remember. Now one can, define another loss function. So let's see if there is a, another. Yes, please. How is the learning rate determined? Typically, it will be between 0 and 1. And generally, as I said, you keep it very small. So this is a hyperparameter, that's what we call it, all right? And there is no, no rule which tells you this should be the learning rate. Generally, you have a range of values. As I said, it's 0.1. So you experiment with 0.1. If that doesn't produce good result or quick convergence, you might, go little down, or you might go a little up. All right. So that's how these are determined. Okay.
It should be the same.
Pardon?
It should be the same for all the examples.
Yeah. It kind of relates with the examples. If the examples are simple, if the boundary is linear boundary, very simple, whatever learning rate you produce, more or less everything will work. But if you have a highly nonlinear boundary, some learning rates might converge very slowly, because you have to go through this process again and again. All right. So if a learning rate is not proper, it might converge very slowly. Or if the learning rate is high, you might be jumping back and forth. Think of an criterion function which is basically has a bowl shape. All right. So, and you are trying to come to the bottom of the bowl by starting at some point. All right. So if every time you move, you take a large step, when you are close to the bottom, your large step might take you to the other side. And when you take a large step from the other side, you might jump to the other side. So you might never go to the actual minimum, or you might take a lot of time to reach the actual minimum. So depending upon what learning rate you have, you might, converge very fast. You might converge very slow. And sometimes with a large learning rate, remember, the activation functions are S-curve, all right? So what you want to operate not in the saturated area, but you operate somewhere in the middle of the curve. So if the learning rate is very high, immediately you will move to the saturated area on the top or on the bottom. And once you are in the saturated area, the gradient values will be very, very small, and you will be kind of stuck there, and it will be a very slow process to come out. All right. So typically you start with, reasonably small value, as I said, 0.1 or so, and experiment with that and see how things are. So it's a kind of trial and error. There is no formula that I can tell you, okay, this should be the alpha value. All right. It comes by experience, little trial and error. All right. So that's okay. So let's look at redefining the loss function, or you can say, well, is there any other way we can define the loss function? All right. So let's modify our mean square loss function. In the mean square loss function, what we did is we took the output of the summation unit and compared that with the actual, with the desired output. All right. Now let's take the output after the activation function. So the output after the activation function is y hat. For the ith example, it is yi hat. And the desired output for the ith example is yi. So now we take the difference between the two, square it up, and sum it over all the examples. All right. So in this case, if we calculate the gradient, we get a slightly different expression as we are showing you here. All right. Now it turns out that we are taking the derivative of yi hat with respect to w. And yi hat involves an exponential function or whatever other activation function you might be using. All right. So if you are using an sigmoidal function, which is shown here as f of z, all right, then f dash g, which is the derivative of that function with respect to g. Basically, if you do the differentiation, that is the expression you will get. All right. So basically, the derivative can be written as output times 1 minus output. So what we will do is we will use this information in our weight adjustment scheme. So y hat is given by this expression if you are using a sigmoidal activation function. All right. So with that, we will get, del yi hat by del w as yi hat times 1 minus yi hat times xi. All right. So for a single example, then this can be written as shown. So what one can do is one can simply look at this expression and you can see that the first term in the expression is yi minus yi hat. All right. We want yi, we are getting yi hat. All right. So the difference is error. So easy to remember, just call this error times yi hat is output. 1 minus yi hat is 1 minus output and xi is the input. So the formula for weight correction with this criterion function is very simple. Error times output times 1 minus output times input. All right. And that is what is written at the bottom. So delta wj. So if you look at the jth component of the weight vector, how that component will get modified, one can write the expression very simply as minus error times output times 1 minus output times xij. That is the jth component of the ith vector. All right. So this rule is known as the generalized delta rule. All right. So basically, previously I mentioned delta rule, and this is a generalized delta rule. All right. And I showed you this for sigmoidal function. If you were using a hyperbolic tangent function, then the derivative of hyperbolic tangent function will be a little different. So the formula will appear to be a little different. So depending upon what kind of activation function you are using, you will end up with either this particular formula for weight change or a slightly different version of this formula for weight change. All right. So let's, with that, let's take an example of, how we can use this. All right. So we'll take a very simple example. So we are given few data points or few training vectors coming from two classes. All right. So basically we have 6 vectors. The first 3 are coming from one class and the other 3 are coming from another class. All right. So y is the array of desired output value. All right. So we can say that for first 3 examples, we want the output to be 1. For the other 3 examples, we want the output to be 0. All right. So there are 2 classes, 0 and 1. All right. And in this case, I have already, augmented the input example. So you will see that every example has a 1 at it, the first entry. All right. So the examples are already augmented. So we don't need to really do about that. All right. Let us see, we choose a delta learning rate of 0.8 0 to 5. And just an arbitrary weight I selected, all right? And we assume an initial weight value, in this case, 0.3, 0.2, 0.6. All right, so that's our initial weight value or W old, all right? And next what we do is we basically go over these examples, calculate the weight change that we need to make, change the weight, and repeat this process, all right? So that is what we are doing, okay?
What is the use of augmentation?
Pardon?
What is the use of augmentation? What will happen if we do augment, like we don't put one every time?
We augment you have to do because the bias term has to be taken care of.
What is the bias?
I'm not getting a question.
When is the bias term?
First term is the bias term, right? As I said, you can put a bias term right in the beginning as a first component of the vector or as a last component. You decide whether you will put it in the first or in the last, but you have to be consistent. Okay. And you need to do this if you are, solving the problems with a calculator or like this, you're writing your own code, all right? Once you have a very large training set, and if you want to use the sklearn library, then the library itself will do the augmentation. You don't have to do it. But if you do something like this, you have to do it, okay? So basically, we gone through all the examples, we get the error, make the weight change, and repeat this process, all right? So basically, what we are doing is we are printing out as we go through the values of error, etc., all right? So you can see that error is going down, all right? And at some point, we decided, all right, that's enough, well, let's stop, all right? So what we have done here is we have calculated, what are the weight values and things like that, all right? So once we get the weight values or weight vector, we can actually use those weight values to figure out where is the decision boundary given by that weight vector, all right? So one can do a plot of that, and that is what I'm showing you here. So basically, we are showing you the examples from two classes with different colors, and the blue line is the line that our method has figured out to separate these examples from two classes. All right? Any question? So basically, you can see it's a very simple process. You specify what you want at the output, what the system is producing, you get the error, and use that error to make adjustments. And you do it again and again till you come to a stage where the error value is either very small or you have gone through enough iterations, and that's it, okay? All right, so what I showed you was how to train a single layer neuron, either using LMS rule or using the generalized delta, all right? And now before that, we also saw how to train using perceptron learning, all right? Now let's come to a situation where you want to have more than one layer of neurons, because with a single neuron, as we saw, all we can do is, doesn't matter whether we do error correction or error minimization, we are ending up with a linear boundary. So what we need to do is to figure out a way to get nonlinear boundaries, all right? So to do that, what one needs to do is, one needs to have multiple layers of neurons. So the picture I'm showing you in this slide here is a picture of what we call as multiple layer feed forward network models, or multiple layer perceptron networks. All right. MLP or feed forward network model. All right. So what is the basic idea? Basic idea is that you have an input layer, you have an hidden layer, and you have an output layer. All right. With these three layers, as I showed you earlier, you can get any arbitrary boundary. So you really don't need anything more than this. All right. So one can use such a network to figure out any mapping that might be presented in your training example. All right. Couple of things to note here. Number one, these networks will be using activation functions that are smooth functions. That is, these networks are not constructed using threshold nonlinearities. You will be using either sigmoidal or hypertangent. The reason you want to do that is because you want to use some kind of error minimization approach from the output to the input side. And for that error minimization approach to work, obviously you need to be able to calculate the gradients. And in order to calculate the gradients, as we saw in the previous slides, you need smooth functions, because if you have a threshold function, then you are stuck, you cannot calculate the gradient. All right, that's number one. Number two, the rule we saw for weight changes was a rule defined for the output layer. All right. Now, when you have a network like this, how do you figure out what should be the correct output for the neurons in the hidden layer? If you do not know what should be the correct output there, how are you going to make the adjustment for the weights over the entire network? All right. So, as I said, these are also known as multiple layer perceptron networks. Another name is back propagation network, because the algorithm that is used to train these networks is known as the back propagation algorithm. All right. These networks are capable of generating arbitrarily complex models. Again, the nature of learning, the criterion function that you use is an error minimization learning. That is, you define an error and you try to minimize that error. All right. It turns out that these networks do take much longer training time because of the number of layers involved. All right. Now, there is, given a problem, you do not know how many neurons should be used in each layer, or what should be the size of the network. All right. Again, depending upon the number of neurons you use in different layers, your network will produce slightly different boundaries, obviously. Also, the training time will be a function of the size of the network. So some of those things are learned by experience or by trial and error. All right. What I'm going to do is, let's see. We will stop here, okay? Because I think that's a good point. I don't want to go through the multiple layer network because we'll not be able to finish it in 15 minutes. All right. So we'll stop here and